So today we are going to study about linear algebra. So first we will know what is a matrix. A matrix is a regular array of numbers or functions. A rectangular array of numbers or functions. Matrices let us express large amounts of data and functions in an organized and concise form. So there can be many types of matrices like square matrix, row matrix, identity matrix, upper triangular matrix, lower triangular matrix, and this is basically a row vector in the example where you can see a1, a2, a3 placed in a row. There is also a column vector. So matrices having just a single row or column are called vectors. And the second matrix is a square matrix, which means that the number of rows and columns are equal in number. Next we will learn about the general concepts and notations. So you can see this is a m cross n matrix, means a matrix with m rows and n columns, and we should always remember that rows always come first. This m and n is called the size of a matrix. So the size of a matrix is m cross n. Each entry has two subscripts. The first is the row number and the second is the column number. This a12 is the entry in row 1 and column 2. If m equals to n, then A is known as a square matrix, and then its diagonal containing the entries a11, a22, ann is called the main diagonal of A. And the matrix of any size m cross n where the number of rows and columns is not equal is known as a rectangular matrix. So addition of matrices. Matrices can only be added when the number of rows and columns are equal. That means only the same size matrices can be added, and they are obtained by adding the corresponding entries of A and B. Matrices of different sizes cannot be added. You can see I have given a small example. So multiplication of matrices. Matrices can be multiplied by a matrix and also with a number. When it is multiplied with just a number, this is known as a scalar matrix, and the scalar C is written as CA, where A is the m cross n matrix, and it's obtained by multiplying each entry of A by C, where C is the scalar. So you can see here A matrix is multiplied by first minus, and then it's multiplied by 10 by 9, and if a matrix is multiplied by 0, what you obtain is known as the null matrix. So there are some rules for matrix addition and scalar multiplication. These are A plus B equals to B plus A, and A plus B whole plus C equals to A plus whole B plus C, A plus 0 equals to A, and A plus of minus A equals to 0. And what are the multiplication rules? C into A plus B equals to CA plus CB, C plus K into A equals to CA plus KA, C of KA equals to CK into A. Like you can write it both in this manner. It's a distributive property. Matrix multiplication. So a matrix can only be multiplied when the number of columns in A is equal to the number of rows in B. That means A is m cross n and B is n cross B. Here you can see that the number of columns of A is n and the number of rows of B is n. So they are multiplied. Is equals to C equal into m cross B. So this is the A matrix and this is my B matrix. So they are multiplied by taking the first row of A multiplied by the first column of B, or you can do the opposite, multiplying the first column of A with the first row of B. In both the cases you will get the required answers. So there are some matrix multiplication rules, that is AB is not equals to BA, which is a very important rule which proves that matrix multiplication is not commutative. KA into B equals to K into AB equals to A into KB, which you have seen as scalar multiplication rule. Again, A into BC equals to AB into C. A plus B into C equals to AC plus BC, and C into A plus B equals to CA plus CB. So what is the transpose of a matrix? It is obtained by writing its row and columns or equivalently its columns as rows. That is, you write the rows as columns and vice versa, and the columns are written as row. If A is this, then the A transpose is this. So what happens? The size of the matrix gets interchanged, it becomes a n cross m matrix. Rules for transposition. A transpose whole transpose is basically A plus B whole transpose equals to A transpose plus B transpose. CA, where C is a scalar, whole transpose equals to C into A transpose. AB whole transpose equals to B transpose A transpose. This is a very important reverse transpose property which you should always remember. Now there are some special matrices which you will need: symmetric and skew symmetric matrices. A matrix is called a symmetric matrix if A transpose equals to A, and a matrix is called a skew symmetric matrix if A transpose equals to minus A. Upper and lower triangular matrices. So upper triangular matrices are square matrices that can have non-zero entries only on and above the main diagonal, whereas any entry below the main diagonal must be 0. Here you can see below, above 1, 3, 3 is the main diagonal. Since it's a square matrix, and above that there are numbers, but below that there is only 0. So lower triangular matrices can have non-zero entries only below the main diagonal, and the upper entries should be 0. Diagonal matrices. These are square matrices that can have non-zero entries only on the main diagonal, and any entry above or below the main diagonal must be 0. So diagonal matrix, you can see there's numbers only on the main diagonal, and above and below it should be 0. So what is a scalar matrix? A scalar matrix is then when the diagonal has the same number all throughout. C is a constant number. And what's a unit matrix? When the diagonal matrix is replaced by 1, it's known as unit matrix. If A is any square matrix of same size, then AI equals to IA is equals to A. So next, what's the determinant of a matrix? Determinant of a 2 cross 2 matrix A is A11, A12, A21, A22 is defined as D equals to determinant of A. You have to write it within single line brackets, and it's basically A11 into A22. There is a cross multiplication while finding the determinant. For determinant of 3 cross 3 matrix, you can take the first element A11, and then you have to leave the corresponding row and the corresponding column, and then multiply with the remaining part. So what's a linear system? You must have known a linear equation like y equals to mx plus c. Similarly, here you have a x1 plus b x2 equals to c, where a, b, c are constants and x1, x2 are variables. A linear system consists of more than one linear equations. For example, a1 x1 plus b1 x2 plus c1 x3 k1, a2 x1 plus b2 x2 plus c2 x2 equals to k2, and a3 x1 plus b3 x2 plus c3 x3 equals to k3. Since you can see there are 3 unknowns, x1, x2, x3, you need a minimum of 3 equations to find the 3 unknowns. To find the solution of this system means to find the values of x1, x2, x3 which satisfies all the equations in the linear system. A linear system can have a unit solution, more than one solution, which is infinitely many solutions, or no solution at all. We will be learning about this further. So rewriting the above equation in the form of a matrix, which I just read to you, it's a1, b1, c1 in the first column, a2, b2, c2 in the second row, a3, b3, c3 in the third row, and x is x1, x2, x2. B is k1, k2, k3. So the matrix A is called the coefficient matrix, and the block matrix AB is the augmented matrix of the linear system. So here is the augmented matrix. If all the elements of B are 0, then the linear system is called homogeneous, otherwise non-homogeneous. So this is the row reduced echelon form of a matrix. A matrix C is said to be in the row reduced form or the echelon form if the first non-zero entry in each row of C is 1, and the column containing this 1 has all its other entries 0. That means you can also get a row echelon form, different form. It results from the Gaussian elimination. A matrix being in row echelon form means that Gaussian elimination is operated on the columns. In other words, a matrix is in column echelon form if its transpose is in a row echelon form. So specifically, a matrix is in row echelon form if all the rows consisting of only zeros are at the bottom, and the leading coefficient, also called the pivot of a non-zero row, is always strict to the right of the leading coefficient of the row above it. So the following is an example of a 4 cross 4 matrix in row echelon form, which is not in the reduced row echelon form, as you can see. So many properties of matrices may be easily deduced from their row echelon form, such as the rank and the kernel. You should always remember these two properties, which is the lead-in entry in each non-zero row should be 1. It's called a lead-in 1. And also second, each column containing a lead-in 1 has zeros in all its other entries. Unlike the row echelon form, this reduced row echelon form of a matrix is unique and does not depend on the algorithm used to compute it. For a given matrix, despite the row echelon form not being unique, all row echelon forms and the reduced row echelon form have the same number of zero rows, and the pivots are always located in the same indices. So next we have the Gaussian elimination method. So Gaussian elimination method is the method of solving a linear system Ax equals to b. It's also known as a row reduction. By bringing the augmented matrix. It consists of a sequence of operations performed on the corresponding matrix of coefficients. This matrix can also be used to compute the rank of a matrix, the determinant of square matrix, and the inverse of an invertible matrix. There are basically main three types of elimination methods: swapping two rows, multiplying a row by a non-zero number, adding a multiple of one row to another row. And using these operations, a matrix can always be transformed into an upper triangular matrix, as you can see I have shown here, and in fact one that is in the row echelon form. Of all the leading coefficients are 1, and every column containing a leading coefficient has zeros elsewhere. The matrix is said to be in the row echelon form. The final form is unique, in other words, it is independent of the sequence of the row operations used. So this elimination process is also known as the forward elimination method. Here you can see I have shown an example. Here is the augmented matrix 0, 1, 1. Since there is no x, so its taken coefficient is taken to be 0, 2, 0, 3, 1, 1, 1. And right side I have the 2, 5, 3. Then you have to interchange the first and the second equation. Since you can see the 0 is at the top and 0 is at the left, extreme left, so you bring it to the second row. Then you divide the first equation by 2 and minus 1 times the first equation to the third equation, add minus 1 times the second equation to the third equation. You have to continue this process until you get the leading one and the rest all as 0. As you can see, when I multiplied the third equation by minus 2 by 3, we get this form. So rewriting this in the algebraic form, you have x plus 3 by 2 z 5 by 2. The last equation gives z equals to 1. The second equation now gives y equals to 1 by putting the value of z. And finally the first equation gives x equals to 1. So what is the rank of a matrix? So the rank of a matrix is the number of non-zero rows in the row reduced form of a matrix. It's known as the row rank of the matrix. So then there is a unit solution or a multiple solutions. The equation is said to be consistent, and when there is no solution, the equation is said to be inconsistent. In linear algebra, the rank of a matrix is the dimension of the vector space generated by its columns. This corresponds to the maximal number of linearly independent columns in A, which is in turn is identical to the dimension of the vector space spanned by its rows, which means the number of non-zero rows in the row reduced form. It can also be the maximum number of linearly independent columns. In that case, it's known as the column rank of the matrix. And the rank of a matrix can never exceed the rank of a matrix can never exceed the number of its rows or columns. If we consider a square matrix, the columns are linearly independent, and also only if the matrix is non-singular. In other words, the rank of any non-singular matrix of order m is m. Rank of a matrix A is denoted by row of A, and the rank of a null matrix is always 0. A null matrix has no non-zero rows or columns, so there are no independent rows or columns, and hence the rank of a null matrix is 0. So how to find the rank of a matrix? We have to first convert the matrix into its row echelon form, then determine the rank by the number of non-zero rows. So first you find the rank of this matrix, you convert it to the row echelon form, You multiply the first row with minus 2 and add in second row minus 1 and add in the third row. Next you can see we multiply the second row with minus 1 and add in second row in third row. We get the 0 0 form. Multiplying the third row with half and multiplying the second row with minus 2 and adding in first, we get the 0 0 1 0 1 1 form. And adding third row in first and multiplying the third row with minus 1 and adding in first. So the rank is 3 since there are 3 non-zero rows. Here you can see for the next example its rank is 2 since there are only 2 non-zero rows and the third row is totally 0. So the rank of a matrix, let AX equals to B be a linear system with m equations and n unknowns, and the row rank of A is greater than or equals to the row rank of AB, that means the augmented matrix. This means that the equation is consistent. And if row rank of A less than the row rank of AB, that means the equation is inconsistent. And also if a matrix is of order m cross n, then row of A less than minimum of m and n is equals to the minimum of mn. And if A is an order n cross n, that means it's a square matrix, and determinant of A not equals to 0, then the rank of A is n. And also if the A is of order n cross n and determinant of A is 0, then the rank of A will always be less than n. Next up we have the linearly dependent and the linear independent vectors. So row vector, as you've seen shown you in the first slide, and the column vector. Given any set of m vectors a1 dot 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 am with the same number of components, a linear combination of these vectors is an expression of the form ca1 plus c2a2 plus dot 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 cm am, as c1 c2 dot 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 cm are any scalars. Now if we consider c1a1 plus c2a2 plus dot 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 cm am equals to 0, if all c's are 0, then a1 dot 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 am are set to form a linearly independent set, otherwise linearly dependent. Example, here we can see a1 is 3022, a2 is minus 6, 42, 24 and 54, and a3 is 21, minus 21, 0, minus 15. They are linearly dependent because 6 into a1 minus half into a2 minus a3 equals to 0. How can you find this? You can find this by c1a1 individually multiply c2a2 plus dot 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 cm am. You can see it's coming as 0 and the cj's are not 0. That's why they are linearly dependent. Next up we will learn about the eigenvalues and eigenvectors. Let A be a matrix, n cross n matrix, that is a square matrix. If there exists a real value lambda and a non-zero n cross 1 vectors at x satisfying Ax equals to lambda x, then we refer to lambda as an eigenvalue of A and x as an eigenvector of A corresponding to lambda. If A equals to 1 minus 1, 2, 4 and x equals to 1 minus 2, Ax is 3 into 1 of minus 2. Hence 3 is an eigenvalue of A, vector 1 minus 2 is an eigenvector of A corresponding to 3. So how can you find the eigenvalues and the eigenvector? So Ax equals to lambda x, that means A minus lambda x equals to 0. This is a Hermitian equation where lambda I equals to lambda into 1 0 0 1, which is identity matrix. If determinant of A minus lambda I not equals to 0, then f of equation as a unit solution of x equals to 0, which can be found by equating x equals to 0. However, the goal here is to find lambda, so the determinant of A minus lambda I equals to 0 must be chosen. So considering A from the previous example, this example, if you do A minus lambda I, you subtract lambda from the diagonals, because since it's a square matrix, 1 minus lambda minus 1, 2, 4 minus lambda. So here you can see you have found the lambda values, lambda equals to 3, lambda equals to 2. This in fact are the eigenvalues of A. So considering the two eigenvalues, lambda 3 equals to lambda 2 equals to 2, let us first look for the eigenvectors A for lambda 1 equals to 3. You have to individually put the lambda 1 eigenvalues and then you have to find the eigenvectors. So namely, we want to find x equals to x1, x2 to satisfy a minus lambda I into x equals to 0. So when we subtract 3 in place of lambda from them into x1, x2 equals to 0, we find the value of x1, x2 as 1 and minus 2. Hence, any x1, x2 satisfying 2x1 plus x2 equals to 0 is the solution of the above system. And the set of such vectors can be represented in a parametric form: x1 equals to t and x2 equals to minus 2t for any t belongs to R, or t into bracket eigenvectors 1 minus 2. So 1 minus 2 is basically eigenvector of the eigenvalue of the matrix corresponding to eigenvalue of 3. Similarly, for lambda equals to 2, you substitute it to 0, a minus lambda 2I into x equals to 0, or 1 minus 2. You do it where x1, x2 you get as 1 minus 1. Hence, any x1, x2 satisfying x1 plus x2 equals to 0 is a solution of the above system. The set of such vectors can be represented in a parametric form: x1 equals to x and x2 equals to minus s for any s belongs to R, or s1 minus 1 in vector form. So the final solution is t 1 minus 2 plus s 1 minus 1, where t and s belongs to real numbers.